Welcome back, everybody. A lot of people have been asking for really basic tutorials from the beginning and slow enough for people to understand them, which is completely understandable. So today it's a video about Ollie, just Ollie, and what it is, what it does. Ollie is a debugger slash disassembler. It disassembles and debugs in real time. So when you download it, you're going to have probably an exe, a help file, and a help DLL. That's probably all. Load DLL might be in there, but I'm not sure. It might be. I downloaded this a long time ago. So the first thing, you run it. It looks something kind of like this, but it's more than likely going to look like this. It's going to pop up in a tiny little screen. And yeah, it's going to be all gray. And the ready button is down here. If you notice it, this is the status, what it's doing at this current point. In my videos, it's up here. That's a INI option. I don't know if they've added an option in here for it or not, but let's jump right into options. This right here is your disassembling syntax. The syntax that I am most familiar with is MASM. It's the one that I know how to write and I know how to read. That's the one I feel comfortable with. If you are wanting to see AT&T code, there it is. You can, it looks way different. I've had to deal with it before. It's no fun for me. But then there's, ideal for, and it shows where they came from, more or less. So then there's all sorts of options here that I never use. There's a couple things, but really I hardly ever use. I'm hardly ever in here. One thing that I do recommend you do is go to exceptions. Click ignore also the following, add rain, and you're going to put in 8 zeros. And 8 Fs. What that's going to do is ignore any exceptions. It's just going to send them to the executable. Something that this does is, say I wrote a program and I had an exception that I cause on purpose, and in the handler of it, just before I cause the exception, I start a timer, and in the handler of it, I read that timer. If it's been more than X amount of time, I know that something's haywire, such as there's a debugger attached, and I can say, oh, there's been a debugger detected. That's one way. So we don't want that. We want any exceptions to just be passed on to whatever we're debugging. So this is the window, right? There's all these buttons up here that I also never use because I use hotkeys. This is step into, step over, trace into, trace over. You can do a lot with Ollie, and there's a lot of stuff you can do with Ollie that I've probably never even done. You can do traces, you can do log traces, you can do all sorts of stuff that if I do use it, it's on rare occasion. So first things, let's open an executable, right? So it doesn't matter what it is, just anything really. So this here, this red line, that's a breakpoint. The black is our point of current execution, or the origin, or the EIP. EIP represents the current instruction. If I hit F8, which we remember right here is step over, which step over means execute the next thing, but if it was a jump or a call, it would not go into it, it would go to the next instruction. I'll show this later. So if I hit F8, we go down one and our EIP changes. This is solely for your reference, I guess. Like, you can't read the EIP. That would be really nice. There's a little trick to get your current point of execution, but yeah, we'll get into that way down the road. So first thing you see here is there's not a whole lot of color going on. We do have, this little guy here. The money symbol means that there is something in this program calls this location, and if we right click and do find references to selected command, we see that, well, it doesn't really call it, but there's a reference to it. It gets moved into ESP. This is a jump, and that's indicated by this red down thing here, and these caret things here are landing points for jumps. So this jump right here goes there. It's red if it's going to be taken. It's gray if it's not going to be taken upon execution. So let's get some color in here. Let's right click in your code section. Not in the hex dump, not over in the stack, not in your registers. In the disassembly, in the code, go to Appearance, Highlighting, Jumps and Calls. That's what I use. It seems to be pretty standard. I don't really know anyone that uses Christmas tree. It's too much going on for me, and I don't like it. There's some other memory access. See, I don't know. The one that I use is jumps and calls. You got your jumps, you got your calls. That's the most important things. Everything else is just, what it is. So over here is your addresses. You have addresses here, you have stack addresses. This is data that's at that address right there. This is the hex dump representation of it. And over here is kind of like comment section of what Ollie knows it to be. Like, it knows that this is an address where something returns to something. It doesn't necessarily have to be true. We could just as easily type return and return to that, but anyways, we'll get into that down the road. So then you have, next in the code section, you have your hex bytes, pretty much. I mean, this right here, E8F3550100, means in processor talk, call this address. So let's hit F8 a few times. F8, F8. Okay, so now that the difference between F8 and F7, which is step over and step into, is if I hit F8 here, it's going to go to here and put a breakpoint. Like that. If I push F7, instead of coming here and stopping, it's going to go into that call, which is right here, and that's where it'll break F7. See, now it's right here. And let's just go over some simple stuff right here. This says push EBP. So EBP is this register over here, EBP, and it has 0028FF88 in it. And what that's going to do, push means to put it on the top of the stack. So it's going to take this and put it on the top of the stack. If I hit F8, we see now the top of the stack reads what was in our EBP. Can't talk. Okay, now move EBP ESP means to take the address of the top of the stack. No, it doesn't. Yeah, it does. Sorry. Because ESP is our stack pointer, and that's the address of the top of the stack, and it's saying to move that address into EBP. So if we hit F8, we'll see now EBP is the same as ESP. Had a little brain fart there. And now, again, we see push EBX. Okay, so we're going to put what's in BX on the top of the stack. There it goes. Sub ESP34. What that's going to do is subtract from ESP34 in hex, or 52 in decimal. Tells you that right here. This is your like little information window. Tells you stuff about the current execution. So if we hit F8, we'll see that ESP got subtracted. And now move dword pointer SS local 14 00401150. Okay, that's a lot. So what that means, let's double click it. And now you can actually see what's going on here. Move dword pointer SS ESP 401150. So what it says is move to the dword at the address of ESP 401150. So that was a lot for anybody who doesn't know what we're talking about. What that means is we want to take this value right here and put it into the address that is at ESP. So our address of ESP is here, which is also the top of the stack. What this section of code is referencing is right here, the actual data in it. So if we hit F8, we'll see that. There it goes. And now it's going to do a set unhandled exception filter, and we're going to F8 over that. Now it's going to subtract from ESP4 in hex, which is also in decimal. And now there's a call to some location down here to do some stuff. We're not going to go through that right now. We're going to hit F8 and F8. And now we have LEA, EAX, what's at the address EBP minus 10. Okay, what the heck does that mean? Okay, there's another way to learn what stuff does. Right click, help on command. And anytime you do anything, it likes to minimize your windows. So what that does is load effective address, calculates address of the memory specified by EBP minus 10, and assigns this address, not the contents of the pointed memory, to 32-bit register EAX. Segment register is not taken into account. Command does not check whether pointed memory is available or not. In fact, it just sets EAX equal EBP minus 10. All flags remain unchanged. This command is frequently misused to make quick integer computations that involve several registers and constants, like in the following example. LEA EAX times 4 plus EAX, which is EAX equals EAX times 5. The only drawback of such computations is that they don't set flags. So this is going to put into EAX EBP minus 10. So if we check that out, EBP is this number and EAX is this number. It is going to become this minus 10, F8, and there it goes. So basically, it's saying that you can use it in multiple ways, but it's commonly misused to do quick math without using so many bytes. Now, move, we've learned that already. It has a couple variants, but they're not hard. The first one we've seen already. Put 0 into the D word that's at the address local 4, or EBP minus 10. So, we're going to hit F8, F8, and now it's a little bit different. It's backwards, it looks like. So, move EAX D word pointer DS4430A0. Okay, so what that says is take
the D word that's at the address 443080 and put it into EAX. So if we watch EAX and hit F8, we get what was at the address of 443080. Could we have predicted what it was going to be? Why, yes, we could. We can go right click, follow and dump, memory address 443080, and it's FF. Okay, so these next few we've seen. Now we have another LEA EAX to put EVP minus OC into EAX, like that. Much of the same we've seen already. A call, I guess I didn't really understand, or I didn't explain what it does. So a call is going to, basically, it's a roundabout way of saying jump to this address, but put the next execution's address on the stack, and then go there. So it would be the same as if you could do it. Push EIP +1 and then jump, and then you'd be able to do return. So that's what it does. So we're going to hit F7 and follow this just to see that. So right now we see we have 447000 at the top of the stack. We should, when I hit F7, see 401072. F7 401072. And that is where it needs to return to when it goes back from the call. Because the call is like going out to a subroutine, doing it, and coming back. And right now it's a jump to get main args, and that's not long, so we're going to do it. And we're going to hit F7. And now we're going to hit F8 through this whole thing here. If there's anything new, there's a couple things new. Okay, so compare D word EBP +14 with 0. So what this is saying is compare what's at the D word, or the D word worth of data at EBP +14 to 0. D word is this much right here, 4 bytes, then a byte and a word. Keyword is 8. So it's saying compare the first 4 bytes from the address EBP +14 to 0. And then it's going to pop ECX. What is that? What that means is take what's at the top of the stack, off of the top of the stack, and put it into ECX. So we should see this go to here, and this go to here. F8. And we do. Jump if not equal, the jump is taken, and it's going to go clear down. We're following this red line, but we can just hit enter and it'll take us to the bottom. And it goes to a call, which calls here, and I don't want it to do that, so I'm going to cheat and say set new origin here by right clicking and doing new origin here. And now we're going to hit F8, return. What does that do? It jumps to whatever's at the top of the stack. So 401072, which is right after that call that we went into and followed. So let's see here. Let's go over test EAX, and then we will go over a couple more things and call it good for now, and we'll pick it up with a actual program and actual reading a little bit later. So test EAX, or just test, basically it's going to say, is it or is it not 0? And if it is 0, it's going to set this bit to 1. If it is not 0, it will stay 0. So if we hit F8, you see that it was 0, so it set it to 1. And if it wasn't 0, we jump out here. But since it was 0, we're not going to jump. J and E, jump if not equal. So let's see what the help says test EAX does. Sets flags according to the result of bitwise logical AND between the contents of 32-bit register EAX and the contents of 32-bit register EAX. Both operands remaining unchanged. Flags C and 0 are always cleared. Command test EAX sets flag Z if EAX is 0 and clears it otherwise. So, yeah, if it's against itself, the mathematical way of looking at that is, let's say we had a number in EAX that was represented by 32 in hex. In binary, that's somewhere I can see it. One one 0 0 1 0. Now, if we had 0 0 1 1 0 1 in another register, which is hex D, then the result is going to be 0. Because an AND in binary math works like this. Are they both 1? No, it's 0. Are they both 1? No, they're zeros. If you had something like this, then you would have 1 0 0 0 1 0. Because they're both 1, it's 1. Otherwise, it's 0. If they're both 1, it's 1. That's an AND. An OR works like this. In this situation, we would see, is one or the other one 1? Yes. Yes, 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 and yes. Okay. But if we had something like this, actually, let's change this. Okay, so now, is one or the other but not both? No. Yes. Yes. No. Yes. I mean, yes. There we go. So, one or the other but not both in either direction. XOR is an exclusive OR that works a little bit different, except I might have just explained it. Let's see. Right. Okay, so XOR is like this. So if we take the same one, XOR is exclusive to only is it one or the other. So if it's both, 0. 1, 1, 0. 1, 1. And in OR, that would be 1 as well here. I explained XOR first, and then I explained it again, and then I corrected my OR. Sorry about that. I very rarely use OR. I use XOR a lot, I use AND a lot, I use NOT. NOT is, hey, take the opposite. So you end up with this. If you NOT that, then you get this. Yeah. Also known as inverting. Okay, so now let's go down to this procedure. New origin. It's going to and what's in ESP with FFFFFFO. So let's actually do that on paper. Grab our calculator, hex, edit, clear, edit, paste, binary, edit, copy, notepad, paste. Now what's in ESP is calculator, hex, clear, edit, paste, binary, edit, copy, and paste. Uh-oh, it's not long enough. We need some leading zeros. There we go. So, if we do an and on these, we're going to get 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0. And that, in hex, is going to be 28FF30. Okay, so we'll do it, and it didn't change. Then it does a call again to some other subroutine, and I think that's where we're going to wrap this video up. And I'd love to have some suggestions for our next video, and if I don't get any, we're going to go over the other bitwise operations, how they're useful, and loops. We're going to write some loops and read some loops, and what they're actually doing, what to look for. And then we're going to read some code in some simple programs, and how it compares to C++, or C probably. More likely C, not C++. And then we're going to move on to some very basic keygenmes and crackmes. And then we'll slowly probably work our way up into more advanced as we go. But for now, we're going to call it quits, and thank you for subscribing and voting and commenting, and I appreciate anybody who becomes a new subscriber. And I just broke 1,000, by the way. That was a goal. And yeah, let me know what you think and where we should go from here, and if not, then I do have a plan. And I'm going to try and get at least one video per week, and at the very latest every other week. Thanks for watching.